تمام دكتور علي.
تمام يا
واضح.
دكتور ايمن. تمام السكرين واضحه، لو حضرتك تعملي ماكسمايز يبقى تمام.
رحت لي. أوكي. السلام عليكم جميعا، مساء الخير.
مساء
وسعيدة
النور يا دكتور أيمن.
سعيدة بوجودي معاكم وتشرفوني. سامحوني لو صوتي مو واضح. هو الزكام جاء فجأة للأسف.
الف سلامه لحضرتك، الف
طيب،
سلامه يا دكتور ايمن.
يسلمك.
تسلمي،
إن شاء
شكرا.
الله تكون محاضرة خفيفة وبنفس الوقت مفيدة.
ان شاء الله باذن
فنبتدي إن شاء الله. بتكلم اليوم عن Basic Science of Pets. باخذكم برحلة سريعة إن شاء الله عن الستبس للبيت سكان، سواء بيت سي تي أو بيت ام ار. ف in this presentation I will highlight the process of PET scan and a PET detection mechanism. First of all, the radio tracer, PET tracer, is being produced using the accelerator, which is cyclotron in our case. Then this radio tracer is being labeled. The labeling being done in the chemistry module, of course, to have the radionuclide labeled with um, the desired radiopharmaceutical, such as FDG, sodium fluoride, gallium dotatok, or dotatate. After labeling and dispensing the end product, it has to be dispensed via vial or syringe and then being given to the technologist to be injected to the patient. After injection, the patient should go through the scan. The patient will be the source of radioactivity and the machine will have the detection process. After detection of beta emitter, of course, as we can see here, and I will highlight later, the image reconstruction will happen, and then at the end we will have the PET images as fused also PET CT or PET MR images. So these are some examples of accelerated charged particle nuclear reaction for producing radionuclide of interest in nuclear medicine and positron emission tomography. Commonly, they are using now the fluorine and gallium. Fluorine as a result of O18, bombardment of O18. We can have ammonia also, but it's very short half-life. Not all sites using ammonia because of the very short half-life. And also bombardment of zinc. Recently, we can have target in cyclotron giving us gallium instead of generator. So cyclotrons can be classified according to the maximum achievable energy for proton beam energy. We have small, medium, and large cyclotrons. Small cyclotrons accelerate to energy from 3 to 13 mega electron volts. Medium cyclotrons from 13 to 20 mega electron volts. Large electrons up to more than 20 mega electron volts. So small and medium energy electrons are typically used in bit tracer production. Large cyclotrons used for SPECT tracer production. Cyclotrons producing proton beams of several hundred mega electron volts are used for proton therapy and radiotherapy. So in a very basic way, this is the cyclotron. This is the ion chamber. It's an open cyclotron, beta trace 800 GE. This is the ion chamber, okay, and this is the targets outside, you can see. And here we are mounting the whatever we want to fill the target, okay? So cyclotrons are used to accelerate particles such as protons and neutrons to high energies, up to 10th of mega electron volt. For example, in our site, we have the beta trace 800, it's up to 16.5 mega electron volt. An alternating electric field, which is RF, applied to the D electrodes in the presence of strong magnetic field causes the ions produced by the ion source to spiral towards the edge of the cyclotron. As the particles are accelerated and gain energy from the D's, extraction system extract the beam into the target. So the idea is that we have ion source here in the middle of the ion chamber and the ion chamber under vacuum. and the ions will be in the spiral path, as we said. And then I need the beam to point it to the target. So we need to have extraction system here. The beam will go through the extraction system and will point it to the target. The target will be filled with the material that I need to be bombardment. So the operator knows how much time he needs to do the bombardment, because during installation of cyclotron, we do estimation of the yield. So after 1 hour, for example, I can have 5 curie, for example. In our site, after 2 hours of bombardment, we get 6 curie of fluorine at the end. Okay. So this is the ion source, much more picture of the ion source. You can see here the cathode and the anode. From where we get the ions, we get it from the gas through that flow through the ion source, uh, like the hydrogen gas. Okay, so applying the voltage between the cathodes, it will ionize the gas, and then we will have the ions. And this is a very simple way. This is the target body. The typically, as you see here, only mounted, but this is the target. Okay, this is the target chamber. This is the way where we place the material inside. Let's say the liquid. If we need to get the fluorine, we will fill it with O18, and it's very small chamber. It's from 2.1 to 2.5 milli only. So after finishing the bombardment, this amount of liquid will be transferred to the chemistry module, and the labeling will happen, and then they will send it to the dispensing unit, where dispensing will take place, and the end product will be in our hand for the patient. So now we have the bit tracer. Okay, so the bit tracer we are using for radio-labeled pharmaceuticals being used to image physiology and function in vivo. And the bit scan measure the activity distribution of beta emitting radioisotope. Okay, what is the idea of beta decay? It's unstable nucleus converts. It's unstable nucleus converted into a neutron. Sorry, It's start with a neutron deficient isotope, decays to stable form by converting a proton to a neutron and eject a positron to conserve the electric charge. Once emitted, the positron will have a number of interaction with the neighboring nuclei, losing energy on its path. Eventually, it will interact with electron, and it will lose energy, and annihilation will happen. We will have the two photons, gamma photons, with 511 kilo electron volts, 180 degrees. So input individually, these two photons are known as singles, and because of this annihilation line, we can know the line of flight. Okay, now what if we have a detector? We had the radioisotope. Now if we have a detector around this radioisotope, what will happen? So actually, if we have a detector A or a detector B, detector A will receive one photon, detector B will receive the second photon within certain time. This is what we call at the end coincidence event. So the detection of two photons at the same time is known as coincidence imaging, with the line between the two coincident events known as the line of response. This is an ideal way, actually, but in practice, it's not happening. Not all the events will be true events. That's why when you see the scan, if you ever see the scan in real time, you will see a true coincidence, scatter, and random, and some numbers will come. Because typically we need all to be true, but in reality, not all are true. There are scatter and random coincidence. The random is two independent distinguishing have photon detected at the same time. The scatter, if one or more of the emitted photons are scattered, the line of response will be misplaced, leading to the scatter. Of course, correction has to be done in the algorithm to overcome this error. So this is positron emission tomography. This is a typical ring detector of PET modality. A typical PET scanner, instead of pairs of detectors, we have a ring of detectors for every transaxial slice through our project. Grouping detected lines of response, you can see here, grouping detected lines of response for different angles provide us with projection data. Once we have these projection data, we can then perform tomographic reconstruction to determine the transaxial activity distribution. Okay, in PETs we have electronic collimation, which is greatest advantage is the high sensitivity of PETs. And this is the picture of a gantry of PET exposed. You can see the block of detectors. These are examples of PET-CT imaging, which is used in glucose metabolism, hypoxia, cerebral amyloid. Again, I want to highlight the detectors. This is more exposed gantry of PET. You can see the detector as blocks. Actually, the scintillator detector that make up the ring known as a block detector. Each has 4 photomultiplier tube. These photomultiplier tube allows the position, energy, and time of gamma ray interaction in scintillator to be determined. The scintillator material most commonly used now is LSO or LSYO, sometimes they call it. Why? Because its high effective density coupled with very good light output and timing properties, resulting in high spatial resolution, sensitivity, and temporal resolution. Detectors have a thickness, okay, a range of 1.5 to 3 centimeters to have sufficient stopping power for 511 kiloelectron volts. Of course, the recent or the modest scanner has the time of flight. Why? Because it gives us the better signal to noise ratio. It will use the time between the two photons to better detect the annihilation location. So it will be better signal to noise ratio. This is a typical design of PET-CT scanner. You can see the CT gantry will be in the front and then the PET. The patient will do the CT scan first. It will not take too much time because of the development of the CT. Recently, we have 16 slice and 64 slice as well. So the scan of the CT to the whole body for the PET CT patient will be from 1 to 2 minutes only. And then the patient will go inside, the table will go inside more to get to the PET area, and the PET will start to do the acquisition. So even the PET scanner have been more dramatic improvement in the performance over the past decade, as with the CT, both in hardware, software, new scintillator as we highlighted, and better spatial resolution, higher sensitivity. Okay, I just need to tell you that patient port is 70 centi, just to reduce the claustrophic effect of extended gantry dimensions, because some patients, they will refuse to go in such scan. Attenuation correction being done in PET-CT, of course, we are using the CT for the attenuation correction. The CT scan is acquired before the PET, as we said, so the attenuation correction factor can be generated during the PET acquisition for the entire volume, which also saving a lot of time. Direct translation from CT house field unit to PET attenuation using the bilinear relationship. So here are some modern PET CT's modalities: biograph, discovery, and Gemini. If you can notice, all of them have the LSO or LYSO, and the port always the same, approximately. So why BITMR? Because of the success that we faced during the PET-CT and SPECT-CT, BITMR became in the field. But firstly, they used the BITMR only in research, especially on animal. Why? Because they could use a low magnetic field. When they want to do it for the clinical trial, of course, they have to go for high magnetic field, up to 3 Tesla. So the challenges have become um, in combining the PET to MR and vice versa, because of the presence of magnetic field, of course. So the what was the solution? They in in history, they wanted to make the two gantries with a distance, or they wanted to shield the PET detector. But the most proper solution at the end was the introducing of a new detector compatible for MR. So of course, CT is a big role in PET-CT, but there are applications, for example, brain, breast, prostate, and abdomen, where the additional information delivered by CT is limited. So MR offers better soft tissue contrast, and also the dose being given to the patient during the PET-CT scan will be vanished in MR, because MR will not give a dose to this patient. Um, so this is where the BitMR came an idea. They have the magnet with the detector in the same time. So all the commercial designs available so far built on the idea of having the two at the same time. These are the detector type that they produced. Solid state semiconductor photodetector, such as avalanche photodiode, silicon photomultipliers. They are insensitive to high magnetic field, but of course they are expensive. As I mentioned, the most human PET-MR scanner have been developed around 3 Tesla. Attenuation correction in PET-MR it's not straightforward, of course. It's challenging. So these are the type of attenuation correction. It's a template-based attenuation correction, atlas-based attenuation correction, image segmentation, and most recently, artificial intelligence. You can see here a modern BIT-MR modality and the silicon photomultiplier, sorry, the silicon detector here. So I believe I reached the end of my presentation very fast. So thank you all.
اوكي، ثانك يو دكتور ايمان. شكرا للمحاضره المكثفه كده والبيزكس اللي خدناها.